All right, hello, everybody. Thank you, Shangri-La. That was a wonderful introduction. And also thank you for working with me on this project and being so helpful in teaching me what qualitative research is about and reframing my perspective on studying in that regard. And so today I'm going to be presenting about adoption readiness in regards to porous concrete in Olympia, Washington. As I'm sure you all know, Olympia is a pretty rainy place, and because of that, it's a pretty rainy place and for a significant portion of the year. Something that you may not know quite as well is that climate change projects these rain events to increase in intensity into the future. And this increase in intensity is only going to further the burden that rain runoff poses on the drainage systems that manage it and the waterways that it spills into. In an effort to address these issues, I decided to try to understand how people in Olympia perceive green infrastructure, more specifically porous concrete. These are the main reasons I chose. There are two main reasons that I chose porous concrete. The first is that the context through which it acts as green infrastructure is rain related, which is extremely pertinent to this area, like I mentioned. And then the second is access to it. I live in a townhome where my parking lot is a porous concrete drainage system. And so I've been able to witness firsthand its ability to absorb and manage runoff and mitigate the issues associated with that. It also slows the process in which water goes back into the ground. So, why am I studying this? What's the issue here? Well, in urbanized areas like Olympia, significant portions of the developed infrastructure are covered in impermeable surfaces, which, like the name implies, doesn't allow things like rainwater to pass through them. This means that as it rains, the water washes over all of these surfaces and gathers and then transports contaminants from these surfaces into drainage systems and therefore nearby bodies of water. In Olympia, from what I observed, roadside drainage systems almost never include any kind of filtration or cleaning mechanism. And so the congregated contaminants oftentimes wash directly into the bodies of water and have known impacts on the biology in these areas. One popular example of this is in regards to 6-PPD quinone, which is a tire preservative chemical that they have ample evidence is like a deadly threat to coho salmon. And so, And so in areas where the drains are also clogged or there's no drains present, you often encounter large puddles of standing water, which can, like pictured here, obstruct roadways and do damage to the surrounding plant life and lawns. Not only that, but standing water is harmful to pavement itself. It breaks down binding agents and can generate potholes. And the hydraulic force of driving over puddles that stand on the pavement pushes the water into existing cracks and crevices and makes them deeper. And so one way to possibly address these issues is with this technology called porous concrete. Like pictured here, porous concrete exists with a series of layers. And I actually have a video. This is me in my driveway. This is like 40 ounces of water, and I pour it, and it doesn't flow over, it absorbs into it. And you can actually hear the crackling of it passing through the pores. And so this is an example of sort of how it works in real time. And as it compares to traditional concrete, which obviously everybody knows, it just passes over. So this is an example of the first known function of porous concrete that I'm going to talk about, which is something called peak flow attenuation. This basically means that the concrete acts as a sponge, and water that would otherwise gain traction passing over absorbs into the concrete and then passes into like a saturated area, like what's pictured here with that white pipe in the middle. And that system allows water to re-enter the drainage system at a much slower rate, which really lowers the burden on storm drain systems. Another key function is pollutant removal. Porous concrete systems have been shown to trap contaminants through the porous structure of it and the small passageways, which then can be pretty easily cleaned using like power washing and street cleaners to restore like 99% of function for up to a couple decades. And the other way that it removes pollutants is through the point I talked about first, because by slowing down the water, its ability to push things through is lessened. And so heavier things and larger things come to rest more quickly when the water moves more slowly. So the last two I'm going to talk about are evaporative cooling and road noise reduction, which I encountered in my research, but to a lesser extent. Basically, evaporative cooling is facilitated by the moisture present in the concrete saturated zone. It cools the concrete as it evaporates, which could potentially help with heat island effect. And then it reduces road noise in some cases because less air gets trapped between tires and the surface due to the porous structure of it. So now that we have a sense of what the issue is and we have a sense of what a solution might be, this brings us to my research question, which is what are the levels of adoption readiness in Olympia and how are they expressed in regards to porous concrete specifically? So the theory that I used for this is something called technological acceptance modeling. And what this does is basically, it's a framework that's used in qualitative research to help researchers understand and predict how users come to accept a new technology. 3 of the 4 criteria: perceived ease of use, which is how easy something is to use or how out of the way the user has to go to use it. Perceived usefulness, which is how good at doing the job a user might think it is. So like how does it perform essentially mechanically? Compatibility, which isn't a question of relevance. How relevant do the users believe that the technology to be to what they're doing or the context of the job they're seeking to get done? And then another one that's not pictured here, but I encountered in a different article in my research, is something called internal readiness, which in most contexts buckles down to financial components because it has to do with being how ready the user feels to take on the responsibility of using it or undertake costs of implementing or using a new technology. So with that theory in mind, I designed surveys which had questions that coded for gauging either perceived ease of use, perceived usefulness, compatibility, or internal readiness. And my methods involved going out to 4 locations. So the criteria were integrated into the survey, and I handed them out at 4 different locations: San Francisco Street Bakery, both of the Olympia Food Co-op locations, and then I left flyers and handed out surveys here on campus as well. I accepted responses for 2 weeks, and during this time, participants also had the option to participate asynchronously by scanning that QR code there. And then they could take the survey home on their phone and respond to it then. So methods for coding for the language were done in 2 ways: inductive and deductive. Inductive codes were done beforehand, and they're what I described earlier, which is you set up the coding in the research questions and then use that to filter responses afterwards. And then inductive coding was done in the open-ended components of the surveys, which you then read and interpret and look for emergent themes as a result, and use that as a way of categorizing your results. And so this is one of my first key findings. which is that the deductively coded questions for internal readiness show high levels of acceptance, with no respondents claiming that they strongly disagree with any of the statements, which is the first three on the left are related to internal readiness. And then the two in the middle are related to compatibility. And then the three on the right have to do with perceived usefulness, or perceived ease of use, I'm sorry. So this shows that in contrast to the first three also, perspectives regarding aesthetic value and quality of life, which are the two in the middle, had more mixed results, which may imply that people are more focused on practical functionality of a technology like this than its value of personal engagement or enjoyment with using the product, or aesthetic value or something like that. The three graphs on the right are responses related to perceived ease of use. And one thing to note is that the last question gauged perceived usefulness by asking like a negative question. So the reason that there's so many people strongly disagreeing with this one is because the question actually says, do you agree or disagree with the challenges of porous concrete installation or maintenance being overwhelming? So more people strongly disagreeing with that indicates that they don't actually find it to be something that would be overwhelming. Let's see. Another way that compatibility was measured was through asking about perceived relevance among the participants. And as you can see, standing water, peak flow attenuation, and pollutant removal have overwhelmingly high perceived relevance. The other two functions of porous concrete, road noise reduction and evaporative cooling, received mostly somewhat relevant responses, but unlike the first three, also received some responses of non-relevance. So there are still a lot of people that find this to be somewhat relevant, but it's also, you have a wider range of opinions where some people straight up don't consider it to be relevant for these two things. Some other key findings regarding internal readiness were phrased in a question that tried to gauge willingness to pay towards the implementation of porous concrete. So almost 48% of people were willing to pay up to $5 extra on the utility bill over the course of a decade to support porous concrete construction. And another 39% of participants are willing to pay as much as $10 in the same scenario. So for future research, maybe some way to get a more granular understanding of this might be to interview more specifically about costs, or leave it open-ended rather than provide a list of restricted options, but have them provide me with a dollar amount. And then the last key finding that I want to talk about is the emergent codes, or the inductive codes, that I found from looking at the open-ended results related to concerns about porous concrete. So most of the concerns related to porous concrete were functionality based or based on payment, which are both sort of physical, real world things that you engage with. And then in the middle, some of the things that also emerged had more to do with how the user personally understands or has uncertainty regarding porous concrete. And so familiarity with it as a concept, and then familiarity with it as its role in like what regulations go around it, and whether or not it needs to be treated as something different from regular concrete, were also something that emerged quite frequently in the open-ended responses for my surveys. So in conclusion, participants showed an overall high level of adoption readiness in the context of porous concrete in Olympia. And the lens through which a sense of adoption readiness comes from focuses heavily on practical and physical aspects of porous concrete. High levels of perceived relevance and compatibility were shown in the context of cost and technological function among participants. Likewise, the majority of concerns were related to either topics of payment or physical performance and maintenance of the technology, although there were a number of more nuanced concerns related to familiarity. Future study could focus on the rate of uncertainty in determining adoption readiness for porous concrete. In a time when adapting to our environment and to climate change is increasingly important, understanding perspectives and values related to technologies that allow us to take these steps towards sustainability is important. Porous concrete is one technology that may allow us to do so here in Olympia. And that is my presentation. Thank you.